Welcome back. I'm Ms. Warnow. We're going to continue our discussion on Matter and Change Unit 2, and today we're going to be talking about energy. Here, energy can take different forms. You can have thermal energy, which should be pretty familiar with. This is heat energy. Electrical energy, flowing electrons, current. You focus on this quite a bit in physics when you take it. And radiant energy is light from the sun. Mechanical energy is moving machines, body parts. You have some type of movement there. Nuclear is stored in the nucleus of atoms. Kinetic energy is energy of motion. And then you have potential energy, which is stored energy. And many of the different forms of energy can fall in one or either one of these categories. And then the one that we're most interested in our particular course, besides thermal energy, would be chemical energy, which is the energy stored in chemical bonds between atoms. And so we focus quite a bit on this chemical energy as well as thermal. The law of conservation of energy says that the amount of energy in the universe is constant. In other words, energy can be converted from one form to another, but is not created or destroyed. For instance, the burning of a match transforms chemical energy into electromagnetic energy and, of course, thermal energy. Thermal energy is present in most of the various energy conversions. The most common energy transformation is taking potential energy and then converting it to kinetic energy. Can you trace the energy conversions that occur starting with the sun's light and ending with hot beans? So you have sunlight here. Well, that would represent radiant energy. Carbohydrates and carrots, so you go through photosynthesis, you get chemical energy stored in the carrots. The rabbit eats the carrots, and then you get mechanical energy here. Same scenario, you start with the sunlight, it's radiant energy, go through photosynthesis, you get the plant here, which has stored energy, form of chemical energy, and then when the plant decays and becomes fossil fuel, you get kinetic energy as the car moves and drops. Thermal energy with heat can be transported via three possible pathways. You can talk about convection, conduction, and radiation. Convection is transfer of heat energy in a gas or liquid, right? The movement is through currents, okay? Conduction is a transfer of heat energy through matter from particle to particle. They're actually touching. So in conduction, you have the actual touching. It's most effective in solids because those particles are packed in tightly together. Radiation is transfer of heat energy by electromagnetic waves. It's the only form of heat transfer that can occur in empty space. So radiation does not require solids, liquids, or gas to do that. And that's how it travels from the sun to the earth, in that empty space there. All right, which image, which each of the methods, it's already said in there. You have conduction, this pot heating up here, convection, hot air balloon rising, and then radiation from the sun. Indicate each method of heat transfer. So you have a picture here, and what we want to do with this picture is decide, which methods here. Here, the substance in the soup or water, whatever it is that's in this pot, that's going to be representative of convection. The pot's actually touching this, this platform here. Right, so that goes on to conduction. And then the platform is being heated in this space here as this heat's moving from here to here. So that's going to be radiation. A beaker on a hot plate becomes warmer. That would be conduction. The pilot light in your car illuminates a map. That would be radiation, electromagnetic. And hot soup transfers heat to the air above it. That's moving through currents. So that would be convection. The specific heat capacity, or simply the specific heat of a substance, is the amount of heat it takes to raise the temperature of 1 gram of a substance 1 degree Celsius. Specific heat is not influenced by the amount of matter, therefore it is an intensive property, right? And so just to repeat that, it's the amount of heat, that's the Q, it takes to raise the temperature of 1 gram of substance 1 degree Celsius. And so over here tells you what each one of those are. That delta T, anytime you see that little triangle, means change in. And so since this is delta T, it means change in temperature. Right? Therefore, the units for specific heat is joules per gram Celsius, or you could also use a calorie there. And so you need to be aware of this equation. When we rearrange, use a little bit of algebra, we rearrange it, and we get MC delta T. And this is an important equation. Q equals MC delta T. Some substances, such as metals, have low specific heat. This means it doesn't take a lot of energy to cause the temperature to change. So low specific heat doesn't take a lot to change the temperature. Other substances such as water have high specific heat. It takes more energy to cause a temperature change. Right? So we would like for you to know low specific heat, not a lot of energy to change the temperature. High specific heat takes a lot of energy. On a summer day, why does the concrete deck around a swimming pool become hot while the water stays much cooler? Well, if we look at that, water has a higher specific heat, meaning it would take more energy to observe a temperature change in water than in the concrete. How much thermal energy in joules is needed to raise the temperature of 50 grams of water from 14 to 83 degrees Celsius? Right, so if we look at this, we'll have Q equals MC delta T. We want to write our equation. We're looking for Q. The mass is 50 grams. The specific heat we get right here is 4.18 joules per gram Celsius. And then the change in temperature, remember, is TF minus TI. So that change in temperature is going to be 83 minus 14, which equals 69. Put that up here, 69 degrees Celsius. So we'll take 50 times 4.18 times 69, and we get, this is what you get in your calculator. Or we're going to pay attention to significant digits. This one has 3, this one has 3, this one has 2. So it'd be 1, 4. So it'd be 14,000 joules. Okay. If 125 grams of ethanol at 25 degrees gains 3,540 joules of heat, what is the final temperature of the ethanol? And it gives you specific heat of ethanol. So we're like Q equals MC delta T. We know that Q is 3,540 joules. We know the mass is 125 grams. We know the specific heat is 2.44 joules per gram Celsius. And then what we're looking for is this TF. We don't know what the final temperature is, but we do know what the initial temperature is. So here we're going to be doing a little bit of math. So we're going to take the 3,540. We're going to divide it by 125, and we're going to divide it by 2.44 to get this. All right. And so when we do that, this side, you end up with 11.6 degrees Celsius is equal to TF minus 25. And so then we bring this over, and then so TF is going to be equal to 36.6 degrees Celsius. So this is a little bit of algebra here. You want to make sure that you're paying close attention to that. Rework this problem. If you are confused on any of the math I did, please come to class and ask your teacher. This actually concludes this second unit on matter and change. Come to class with good questions tomorrow. Thank you.